Hello everyone, and welcome to our third day of working with UNIX. Today we are going to talk about working with the queue. So let me share my screen with you and let us proceed. All right, here we go, and put the slides up. This is the third day in our three-part series. Today we're going to be talking about bash scripting, understanding the queuing system, creating bash scripts and submitting scripts to the queue. And in the course of doing this, we'll also talk about some more UNIX commands. So we've been talking about the compute nodes. These are the queues that we have talked about: HP12, MVGPU, MW256, TinyMem, MW128, AMBER128, and EXX96. And so what we'll be talking about today then is how we can take these scripts and be able to configure which of these queues we want to run on, and understand a little bit about what this information on this table is going to be telling us about how we need to set up our configurations for running our jobs on each of them. So let's start out by getting started with some scripts. So just to get started in the scripts, we need to talk about the use of pound. So the pound is in fact actually used for comment in general in the bash script. And the job submission scripts are going to make use of that in a special way. They're going to use the pound in order to indicate some information about the parts of the script that are not to be interpreted as bash. They're going to use the pound symbol in order to indicate the B sublines. So the B sublines, as we'll see, are going to be telling us information about how to actually configure the job. We also have the pound symbol for indicating the shebang line, which is going to be used in basically any scripting language in the UNIX environment. And what that's going to do is that's going to be being used to indicate what should be interpreting the script that you wrote. So let's take a look at the shebang line. So this is an example of a shebang line. Notice that it begins with the pound symbol, and then we have the exclamation. So the exclamation is the bang part of this, and this says bin/bash. So if we're using bash shell scripting, we need to indicate where it should be looking in order to run this script. So this says this is a bash script, so you should be using the program that is located at /bin/bash. So notice that the first slash means root. So you can in fact actually CD to that location, change directories, and actually view that that's where the executable code is. There could be other things indicated here, and so there are other programs, C, C#, Orange Shell, and so forth, Python, many other things. And so depending on what kind of program you've written, you would put a shebang line there to indicate where the thing that should be running it is located. So the pound symbol here, being in general, having the use of being a comment, is going to indicate it's not to be directly interpreted as part of the program, and then being in the location of the first line, that and having the exclamation point at the beginning is what is going to make it be used in this particular way. So the indication here then, of course, is going to have to be a path, as we said, and then this will need to be pointing to whatever needs to be running your code. So this just gives you an idea that the shebang line could point to something else. So we'll be using the one that I showed you for our scripts because we're writing bash scripts today. But just to give you an idea as to how you would figure out what to put on another program, I'm going to show you this. So it could point to something else. Now, it shouldn't be pointing to just any program. It should be pointing to the thing that's going to run the code that you have. So we're pointing to this bash right here. So the /bin is a typical choice for where you're going to find executable code. And so there's also user local is another common place to find executable code. So you could point to /bin/bash, but you wouldn't point to any of these things, like you wouldn't point to gzip, right? That's a program that zips files. You wouldn't point to that in your shebang line because that gzip doesn't actually execute like a program. It's not a programming language, right? So that's why you wouldn't use that one, but there could be other programming languages in other places. And so here, this is just showing you where it's located, right? So when we had the /bin, so you see I'm doing an ls of /bin, that's how we can see it, and then the /bash. So when we pointed to /bin/bash, this is the /bin location, and then bash is the program in it. So we would cd to the bin and then look at the program. So suppose we wanted to select a particular version of Python. So we notice that both Python 3 and Python 2 are available on the cluster, and we can find that out using the which command. So you can use a which and then give the name of what you want to run, and it will report back all of the different things. Will report back the location of where it finds the thing that you're looking for. So if you want to know what will execute Python, you can do which Python, and this gives us the path to where Python is running. And we notice that this happens to be by the default version of Python, because you know version is indicated here, and this is version 3, which is the latest version of Python. This is version 3.5. It's not the absolute latest version of Python, but major version is the latest one. But some people may also need to use Python 2 for legacy purposes. Many bioinformatic tools and so on still use Python 2. So you may want to know if there's a Python 2 on the cluster. And so we see that actually there is, and it's going to point to this location. So Python 3 is the one that's selected if you just use plain Python. So that's helpful to know. That's what you would be running. But suppose you wanted to specify which one you wanted to use based on your shebang line. So how would you do that? So what you can do here is you can put a shebang line in that points to the position for Python 2. So here's the path that we found for Python 2 using the which command, and we put it right here. If you wanted to point to Python 3 explicitly, you could use this line here instead. So you do the pound exclamation, and then you'd type this path shown right here. And so then what we can do is we can verify whether or not this is going to work. And so what I've done here is I've put a print statement in the format that is specific to Python 2, right? So Python 3 uses parentheses for print. And so it should cause an error if Python 3 is executing it. So to verify that Python 2 is actually working, what I did is I then set up my script to run. So we'll talk about changing modes shortly. This is how you run a script. You do the /, and then you type the name of your script. So I called the script test.py, and then we get echoed back on, well, we get printed out to the screen, hello world from Python version 2, which we see right here is what the script is supposed to do. So it worked. File permissions is an important concept in working in the UNIX environment. So users on a cluster are organized into groups, such as labs or classes. And so because it's set up for the multi-user environment, it makes sense that we would want to do this sort of thing. And so basically, for example, in my lab, we might want to have information that's shared among the lab members. So what we would want to do is we might want to have a way to share files amongst ourselves, but maybe we don't want to share with other people on the cluster because, you know, they don't really have a need to see some of our particular programs that we're working on. And so we have this idea of permissions for different classes, people. So everybody should have permission to read, write, and execute their own things. So everybody has control over what it is they create, which you can only create in your own directory as long as permissions are all set normally. And so then what you can do is you can share the ability to do things in your directory with somebody else. Like, let's suppose that my postdoc creates a great script and he wants to share this script with our new students because they don't know how to write the script yet. So what we're going to do is change his permissions so that they have read and execute permissions on his directory. So then other people could do that. So an experiment you can try is you can actually try to change directories into somebody else's home directory, and you'll see that by default you won't be able to go in them. So if you cd to /home and then try to go to somebody's directory, a lot of them you won't be able to do that. You should never give write permissions to other people on your directory for a few important reasons. First of all, because if you give write permissions to others on your directory, then they can fill it up with their junk. And the other reason is because then they would be able to edit your files without your knowledge. So you may not wish for people to do that. So usually the permissions you would be sharing with others would be read permission, which would allow them to open something and look at it, but not edit it, and execute permission if it's a script. So another important point is that execute permission can be added to any file, but that doesn't automatically make it become valid executable script, right? So I could write a text file that says, you know, gobbledygook inside, and if I change it to be executable, it's not going to magically become a program that does something useful. It's not going to be an executable program at all. It's just a text file. So that's an important thing. You can change the permissions, but just because the permissions are set, it doesn't change what it is. So talking about these different groups, then there are 3 ways that the permissions are applied. So if we think about sharing with the group, that means that there's 3 categories here. So there's user, that's yourself. So you can add permissions to you as the user, and so the permission that you would be interested in adding is converting a text file that you made if you wrote a script and converting it into an executable file. So when you write a script, by default, it will not be executable. So you'll need to change your permissions to make it executable. Group is that sharing with others that are assigned in your group. The way you get to be in a group has to do with how you are registered when you become added to the cluster. So the system administrator will assign you to a group, which would typically be your class at Wesleyan, or it could be your research group. Those would be the typical group affiliations you would have. And then O is for other. So other basically means anybody that works on a cluster but is not in your group. And so the permissions that we can add or subtract are R, W, and X. So R is for read, W is for write, and X is for execute. So maybe you want to view the file permissions. The way we can do this is we can do the ls command, which we've seen before, and then we do that with the -L option. And so that stands for long. And when we do that, you see that we get quite a lot more information out here. So if you do ls -L and you don't give anything, it will just show your current working directory. So here are all the files in a current working directory that I'm in. I'm in the workshop directory. And these are the dates of when they were made and the file sizes. This is my affiliation. And you can see what the permissions are. So the first one is actually not a permission. This is whether or not it's a directory. So these are all files. So that's why these are all dash. And then it goes in 3 groups of 3. So first is user. So on this emin1.in file, I have read, write, but not execute permissions because it's not executable. So I didn't change it to be executable. Well, we see this one down here is actually a script, run emin.sh. It's a bash script, and that one has executable permissions. Now, other members of my group can read these files. Actually, I'm sharing all my files with my group, and yes, this is group. And then other people on the cluster have read permission. I would also mention that the permissions that you have set on your directory to get in also is going to affect this. So if your home directory is not readable, then you would have issues with sharing something that's inside it because somebody else who wanted to view your files would encounter that block at that point. So it is a little bit more complicated than that if you're trying to share between people. Right now, we're really trying to focus on what it is we need to do in order to be able to make scripts executable. And so notice that all of these are green, and this is because it's color coding them for you so you know what is executable and not by a quick glance. And so we can see that X is turned on for all of these, and these are all scripts that I have written and turned into being executable. So this is how we would actually make a script executable. If you create a script using a text editor, by default, it's not going to be executable. It's just going to be a text file. So what you're going to do is you're going to use the chmod, and then you're going to pick what it is you want it to be. So you can do chmod, and then you're going to select from user group or other, and then you're going to either plus or minus, and then you're going to pick the permission RW or X. So you can select any number of UGO, and you can select any number of RWX. So here, if we try to execute using the / notation, notice that we're going to get the permission denied error. So here we see that this script is not executable by anybody. And so here we are viewing the file, right? So it's that hello world version 2 test we saw above, and right now it doesn't have executable permissions, and I am looking for my permission right here, which is a dash, so I don't have permission to do it. So what should I do? So to fix the problem, what we're going to do is we're going to use the chmod or change mode command. Plus is for adding permissions, minus is to take them away, and this is a schematic to help you remember what it is you need to do. So you use the keyword chmod, because that's the command. You select whether you want to add or subtract permissions from UG or O, and then we also need to select between RW and X, and then you give the file name. So here, what we're going to do is we're going to add execution permission for the user. So you do chmod, so U for user, plus because I want to add the permission. I would use minus if I wanted to take it away, X for execute, and the name that we want to do it to. So let's make another example. Suppose I want to remove all permissions for others. So the all permissions are RW and X. So I would do chmod O for other, minus for take away, read, write, and X, and execute permissions. And of course, we can verify all of these things have updated correctly. And when you run them, you should verify that all of them are updated by simply using the ls-l to view your files. You can use ls-l in the particular file name, or just do it for the whole directory and find your file of interest. So here I have done this update. In fact, I actually changed the mode so my group members also could execute my wonderful hello world script. And we see that it is again working. So that brings us to bash scripts. So bash scripts are something that are going to be really useful to use. Bash is in fact a programming language, and bash is the language you've been using when you're typing at the prompt. So it gets interpreted by the shell, and then that gets sent to your processor and does what you're typing on a computer. But we don't need to be limited to only typing at the command line, and so we might want to put it in a script. This is a very popular choice of language used with Unix machines. So we talked about how Unix is very important for scientific computing. Bash scripts are one of the most common kinds of scripting languages that can be used, and is oftentimes the default scripting language when you're working on the prompt. Other ones would be the C variants, so which is different than C programming language. It's the C shell. So and also Corn is another one that you may encounter at some point. But in fact, actually all of them are reasonably similar. A lot of the basic commands will work in any of them, but bash is probably the best one to start with. Like we said, you have bash on your command prompt, and you can save commands as you type into prompt into a text file, so then it will be executed at another time, and that's a script. You can write bash scripts to do tasks you would do at the command line, and you need to learn how to do this for submitting your jobs to the queue. So why should we bother to create scripts? I mean, you know, isn't it easier? You just type it. We've been doing that for a couple of days. Isn't that good enough? Well, I would actually argue that there are a lot of really good reasons to write scripts and learn how to do it and do it well. One of the things, it's going to save you an awful lot of time. So some of the things that are going to be beneficial is you'll have a record of the procedure that you ran. So if you need to go back and do it later, let's say, I don't know, maybe you're running a simulation and you can't remember, you know, what exactly was the input file that I used, right? Well, no need to have to wonder what it was. If you simply just run it with a script, you could rerun it exactly because you have your script. It can be run at a later time. So as we start seeing the queue, this will be very important. So if you had to wait for your computer to be ready and then type everything, you could be sitting and waiting at your computer for a long time, and you may not necessarily know when you would need to start typing things. So these work using a script. You can also automate tasks. So there are ways that you can expand your knowledge about working with scripts, and you can in fact use inputs and outputs directly to your script. So if you have to run a simulation, maybe you need to do 10 variants, you know, maybe you're looking at things under different salt concentrations or different forces or whatever your variation is. Instead of typing it out every single time, you may have a standard script that allows you to put the input of whatever your variable is going to be. And so you can automate your tasks. And the other reason is to be able to share with other users. And so this is similar to keeping the record of what you did. You can share that information with others in a way that they could also run it. So let's talk about how to actually create a bash script. So this is part of why we learned how to do working with editors. So you should be using your editor to type your script. And so what you're going to do is you open it up and you're going to create a script, and you'll have the experience of writing some scripts in today's workshop exercises. So although Shebang is not necessary, I would definitely recommend that you put it there. And so for all your bash scripts, this is what it will be on our system. Okay, another thing you want to put is your comments. So these are going to be regular comments, right? And so when you have a comment in your script, it means it's not executed, it's for humans to read it. So then what you're going to do is you're going to enter your UNIX commands in the script. So you'll notice that there are some commands we've encountered before. We have echo, which is basically bash's version of print, pwd for getting the current working directory. And here what we're going to do is we're going to basically create some fake data, but you could imagine that maybe you're going to, you know, run some program that will create the results. Notice the use of this caret, sideways caret, the greater than sign, which is going to redirect the output. So when you normally echo things, where does it go? Well, it's going to go to the screen. So when you run your script, this echo will print on your screen, but this echo is going to instead go into data 1. This double chevron means to append. So what this is going to do is it's going to create a file called data1, and now when we echo something in it and we do this double chevron, it's going to append it on. If we were to use the single one here, what would happen is it would overwrite it. So if we did all of these with a single greater than sign, then we would be left only with 84 in the data. And so use the single one when you want to overwrite and start a new file, and then use the double when you want to append it on. Okay, and then we're also putting the current working directory in the data file, and then we're using ls to display the contents and also to show the contents of data 1. So it's a pretty simple script, illustrates the use of some of the aspects that we've learned so far in this workshop. So then when you want to run the script, we need to make sure that we do a few things. So what we need to do is we need to change the permissions. So the script is executable. So here we're changing the permissions on the script. So this adds execution for our user and group onto that test.sh script. // is what we're going to use in order to actually execute the script. So the reason why we use dot is because that's current working directory, as we talked about when we were talking about the directory trees. So this is another use of the dot for meaning the current working directory. So we say the current working directory, and inside that directory, I want to run test.sh. So that will run this script. And here we have our expected outputs from those echo lines that we had that were going to the screen. If you test this out on your own, don't be concerned if you don't have all of these files in there. I had a few more things that I was working on to make your tutorials and so forth, which is why there's all these other things in here. All right, so that's how to make a general bash script. What I want to talk to you about next is how to make a job submission script. So that's a specific kind of a bash script that is going to be used to send a job for calculation. We talked about the scheduler and how the scheduler is going to take your calculation that you want to do and send that to a back node on the cluster and then make it go get calculated. So what we need to do is we need to write a bash script to configure what it is that it should be doing. So we start off like we do all scripts with the shebang line. So the first line of script is the shebang line. Here it is. And this is a bash script because that's the language that we talk to the UNIX shell with. And so it will be a bash script. That would be a great choice, and that's what we have running on our cluster. So next, we need to take a look at the B-sub line. So the B-sub lines are going to have actually that B-sub, it will actually have, say B-sub, that will be the keyword. And so that stands for the submission script. And so what we're going to do is put the information there to configure various aspects of the resources and the kinds of job inputs and outputs and those kinds of things in the B-sub lines. So the way that we need to separate out the B-sub lines, just like we wanted to separate out the shebang line, is to have a particular convention that will not be interpreted as part of your actual script. So we're going to have a pound in front of the B-sub because it's going to be a comment to the rest of the script, but it's going to have some very particular things. Okay, so for example, you should not have B-sub as variable name in your script, right? Because that's a reserved word for doing something very particular. Okay, so B-sub is going to then be several lines, and we're going to have various flags on it for configuring the different things. So -q is going to select the queue. So we had the list of the queues in the beginning. So what you will need to do is pick which queue you want to use. It needs to match the kind of calculation that you want to do and have the resources that you need. -n is going to be for the number of nodes. So typically, you can just pick one for a regular job. If you have parallel job, you can select some n greater than 1. Obviously, this should be an integer. But what will not happen is just by selecting a higher n is not automatically going to make your job run faster or make it run on more than one node. Your job, so the code that you're executing has to be set up to actually have been parallelized in order for this to do anything useful. So if it's a script that you wrote, so maybe you wrote some program, you're gonna pick n is equal to 1. If you're running another program that you know is written to be parallel and it has that option, and that option is available, and also you'll need to make sure you have the libraries that are associated with that, then you can pick n, some number n, which is greater. Otherwise, you'll just be reserving extra resources on the computer that aren't actually being used. R is going to select the resources on the machine to use. So there are going to be several parts to this line. So GPU is the keyword used to indicate how many GPUs you're requesting. So again, it's sort of like the -n. If your program is set up to run on GPUs, that is the program you actually have is made to run on GPUs because the code calls a GPU, then you can select a GPU and it will make your job run on a GPU. Now you can in fact reserve a GPU and in your calculation never actually use it. And that again is a pretty wasteful thing to do. So you only want to select the GPU if you're actually going to use it. And then the number that you pick needs to depend on whether or not your code is written for one GPU or it's parallel. So these are the kinds of things that you really want to discuss with current users of the particular program that you're working with, and how to actually configure it. So just for example, we're running Amber in my lab, a molecular dynamics package, and we have code that will do all of the above, and there are very different ways that we would configure runs to do each of those things. Run it on CPUs, a single CPU, run it on multiple CPUs, run it on a GPU, run it on multiple GPUs, right? So you have to know what it is that you're trying to do, what your code capabilities are, and what the best way to run your program is. We also have mem. This is going to indicate the amount of memory that's requested. The reason why you need to do this is because then there's what's called the stack, and as your stack fills up with information from your program, this can expand to take up the memory. And so you need to make sure that when you start computing that you have enough space for that stack to expand and not run out of memory. So suppose somebody else were running a job on the same node as you, you're competing for the same memory. So the way that we avoid the problem of two people running on the same location and competing for memory, and suppose somebody uses up more memory than half, right? And you also need more than half. There's gonna be a problem because somebody's gonna run out of memory. So what we do is we do the allocation so that when you run a job, it says, okay, when you get assigned, you get a certain amount of memory, and that's blocked off for your job, even if you're not actually using it in that instant. And other users who may be working on the same node cannot encroach on your memory. And so it makes your jobs more stable and avoids the point of running out of memory. Let's see, and then the span host. This is really talking about if you're requesting multiple things. This typically comes up when you're running the GPUs. And so maybe you're in a situation where you have a job that actually needs more than one GPU to run faster. And so if you are going to request more than one GPU, the host is saying whether or not those GPUs are across different machines or not. So we saw some of the setups of the cluster 2 days ago, and so when you said the host equals to 1, it's saying that if you're using more than one GPU, it's going to be on the same machine. Why this matters is because if you're going between different hosts, the connectivity may be slower between the hosts, whereas the connectivity inside the same host for GPUs is going to be, generally speaking, will be faster. And so you may want to force them all to be on the same computer. So usually you want to select one. Now, if you don't have that problem, or you can't get the resources that you need by changing and by allowing it to go across hosts, it may allow your job to run faster if that's supported with your code. And so, so you may get to calculate faster. You may get it, that means your job may be assigned and actually start faster, but the amount of time to run your job would likely be longer if you're going across multiple hosts. Okay, so more on the B sub. So the next flag is the -J, and that's the job name. You can in fact actually make that any text string. It doesn't really matter what it is, but as a general rule, what we do here is we typically choose the name of the current working directory. That doesn't cause it to go to the current working directory, but that's usually a good indicator as to what your job is about, because you've probably named your directory that way. Also, -J is what your job is going to show up as when we actually go to check whether your job is running or not. So other users will see what you've called your job. -O, that's lowercase letter O, configures the name of the output file. So this is the output from the UNIX system and not the output from any programs that you're running. Sometimes students get a little bit confused about which output file to look at. So that's the system output file. this is whatever would have been displayed on the screen at the prompt. So if you type some Unix command and let's say you make a typo, right, it will tell you something back on the screen. So what will happen to stuff that would have gone to the screen? Well, it gets redirected to the output, and that's why we call things standard out. So standard out usually means your screen, but in this case, standard out then becomes your output file, which collects what would have been on your screen into a convenient output file. -E is going to configure the name of the error log, so your system will also produce an error log from when it runs. So the difference between -O and -E, the output and the error, is that the error log is going to be errors that got generated, whereas the -O is going to be more like a log. So it may have some contents in it that are not necessarily errors, but sometimes the output can be helpful to figure out what the errors are. And if your program is throwing an error, you may, if it were to throw it to standard out, it would show up in the -O, whatever file you configure for there. So what you're putting there is you're actually putting the name of the file, which will contain that information after you run your job. So this is an example of what a bsub would actually look like. So it goes below your shebang line, and then this is a comment. So we're going to say, okay, this is my bsub section, which is useful for humans. This doesn't do anything for the scheduler. Now these here, by having a single pound in front of them, are going to send the information to bsub. And notice that I also have this one here, right? So the reason why I'm doing this in my script is because sometimes I want to run in this queue and sometimes I want to run in that queue, and I'm just keeping this here when I reuse that script. So this one is not going to be used, but this one will be used because this one has a single pound, but having extra pounds will make this be a comment even to the bsub. So here we have the prescribed format for the bsub, a single pound, and then exactly bsub in capital letters. And so now the scheduler is like, okay, this line is for me. And so we have -Q, and then we're going to give the name of a queue here. So again, that off of that list of queues that we saw. Okay, the -N1 selects that it's going to run on one node, -R, and so this is for our resources. So the resource usage is going to be 1 GPU. This is the amount of memory that I'm picking and the host that I'm running it on. So this is for a pretty big job. This is an energy minimization job using Amber is what this is from. And so next we're going to do the bsub -J. So this right here is the name of the current working directory for my job. That doesn't make it go to the current working directory. It's just that it's going to show this is the name of it. And now I've also configured a file which will be called out and a file which will be called error to take my output and error from the system. That's from UNIX. Path configuration, libraries, and environment variables. So this is a kind of a complicated thing, and it's difficult for me to tell you what would be a general one that you would need to use. So these are going to be highly program specific depending on what you're going to use. So for example, if you're running MATLAB and you put in the ones that I show you for Amber, then that's not going to work. So you need to really get the ones that match what it is you need to do. If you are running your own program, something that you wrote, if you didn't write any library dependencies, so like let's say you wrote a simple bash script, then you're not going to need any of these. So this is just basically if you have dependencies on these kinds of things. So they're specific to the program you want to run. If you just have a regular bash program, you don't need them. Programs you wrote yourself are likely to not need them. And so if you knew how to write that in, you probably also already know how to configure that. So if you don't know what that is, then you probably don't need it. All right, so these are just a couple of programs that we have on our cluster that are going to need some configuring of the environment variables and so forth. So like Amber, Gaussian, MATLAB, Mathematica, LAMPS. And so those are the ones you're going to need to just pretty much check with your lab members, check with your advisor. If there's an example script, that's really the best way to quickly figure out what it is you need to put there. So just to give you a little bit of idea of what these things are, the paths are going to be where to look for your program for specific directories such as software's package bin. So we talked about bin a little bit, having executable code. This path will point to the bin of, say, Amber. or Gaussian or MATLAB, so it knows where to actually get the code it needs to run. Libraries are going to provide additional functionality, and so you may have some library dependency of your code if you're using any libraries. These could be different between the machines. So there's some libraries that may pertain to, for example, MPI runs. If you're running parallel code, you may need some specific libraries. And so, for example, if I'm using AMBER 16 versus AMBER 18, I would use different libraries. And if I'm running on different hardware, again, there's also different libraries for that. And depending on whether I'm parallelizing my code by the code itself being parallel, so having threads inside the code, and whether or not I am trying to run it on a GPU, those will all dictate which libraries that I need to configure. So again, make sure you check what you need for your specific program, because it's really difficult for me to say, you know, this is a great setup for generic libraries. There's probably, that doesn't really exist. Okay, and then so the other thing is the environment variables. So you can have variables in your scripts, and an environment variable then is going to be a variable that is going to be set in your script, and this is typically used to contain the information that you've put in your path. So for example, an environment variable may contain a path to a packages bin. And so those are the kinds of things that you would need to set. So for example, we set Amber home in our script. So you may have, I don't know, Mathematica home in your script. So this is an example of what this could look like. So this is the one that we're using in our lab for the Amber 16. And so you see, we have these things. This is an example of an environment variable. So we have a path environment variable, a load library path. So you see that we're holding paths for various different things. Okay, and so they're pointing to particular paths, and you see that it's picking a bin and a library and another bin and so on. And then this is about using that scratch space that we talked about. These are some variables that are involved with using Scratch. And this is also setting up, again, some more path variables that are in the environment in order to make that work. So how do I know which configuration I need to include? So these are just some ideas of who you could ask if you're trying to run something and you don't know what you need to put in for those environment variables and so forth. Ask your research advisor, ask your lab mates, as someone who's running the program that you want to use for a sample script. So maybe another lab has one, or maybe you have some forum on the internet, right? That's another great place. You can look on the wiki for your program interest. Yeah, I mentioned that we have a great wiki for running things on the HPC, which was mentioned, I think, on the first day in this series. So you can go to the wiki and then search for what it is you want to do. And there are many sample scripts available on the wiki. So I would suggest you take a look there. And that may help you get started for getting your jobs to run. Now, if you run your jobs and you're getting errors in your error log, one of the reasons could be that you have not correctly configured your environment and your path variables. So then finally, what we put in our scripts is the job specific command. So this is going to be actually running the program that you want to run. So I want to run, oh dear, this is upside down. All right, I want to run an Amber code, and so what we're going to do then is we're going to put in the command for actually executing that code. Right, so if you have MPI run wrapping around this, you would include the MPI run. If you are having inputs and outputs to your particular file, then you're going to have to work out, you know, how to configure your inputs and outputs. It's likely you may have multiple flags to show, you know, where's your input file. You may have more than one input file, and then you may need to also configure some of your outputs. Suppose I need to test my code before I put it in a script. What should I do? Okay, so you may at this point feel tempted to type your command Like maybe I would type amber, blah, 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 input file, output file, and do this on the command prompt. Okay, so this is really not a good idea. And so this gets back to working on the head node. So remember that the head node, Cottontail, is in charge of doing things for all the users on the cluster. Everybody who logs into the cluster is talking to Cottontail, and Cottontail is also in charge of scheduling the jobs. So if you take your program and you run it on the head node, and everybody runs their programs on the head node will be running all the jobs and not scheduling anything, and the back nodes will be doing nothing. So this is why we really don't want to run things on the head node. Now we realize that people may want to test their scripts before they start putting, to test the commands, because when it comes down to just practical day-to-day stuff, one of the things that you might want to do is, verify that your input worked, make sure that it can read the input file. Have you named all your files correctly? Do you have a path error? Could there be a problem in your input file that would cause your program to crash? And so before you go off and send it to the queue, maybe you want to just test these things out. Okay, so there are some etiquette rules about this. Now, what you can do is you can run some things on the head node. When you're typing something and pressing enter, you're in fact running it on the head node unless you SSH specifically to a different machine besides Cottontail. So that's fine, because that's not going to overwhelm the machine. What's going to overwhelm it is when you start doing your calculations. So if your script runs in under 10 minutes, then it's fine. You can test it out on the head node. I mean, is this a great idea? Well, it's really better not to do that. But, if you need to, and just keep it short. So some of the things you might consider doing is making a short version of your program, instead of, so if I run a simulation that's going to be, 1,000,000 steps, and that's what I want to run. Could I set it up and test out if my input files would work if I ran 10 steps? Well, yeah, because everything would be read in and it would do, it wouldn't carry it out for very long, but it would in fact read through all the input files. And at this level, a lot of times that's where most of the issues come in. And then once it's like processing, then it's not really going to likely encounter problems that it could not read some input file or your input parameters are wrong. You're going to know that right in the beginning. So what you could do is you can make a cut down job that's not going to do all the things, like maybe it won't calculate all the steps, but it's just going to get started. If you could make something that would run in under 10 minutes, probably nobody's going to bother you. But it's really better to run it in the queue. That's really what you should be doing. And so if you really insist on you need to do this, there are some things you can do. So if you must run it on the command line to debug it or test it or whatever you need to do, what you could do instead is you could SSH to one of the back nodes, and then you could work from the prompt. So that's not ideal, because really you should be submitting it to this, you should be submitting your job. It should go through the queue, and that's really what you want to do. But sometimes it's not working and you feel like, okay, you have to do this. So what you can do is you can SSH from Cottontail to a different machine, Petaltail, Swallowtail, Cottontail too, especially if it's going to do something that could possibly destabilize the system. Like what could it do? I don't know. You could use up all the memory, and then Cottontail wouldn't be able to schedule jobs and the computer would crash. And all the users wouldn't be able to use it. That would be bad. So if you're going to do something that you think might do something crazy, point one, check with the sysadmin. He may be able to tell you what to do. Check with others who are in your lab. Maybe they already solved the problem or have some suggestions for you. Or do it on another machine. All right, so suppose I'm logged on to Cottontail and want to test my Sandra run to be sure all my input and output files are working correctly before running a script over the weekend. Well, I'll be away and I need to get my results, but when I submit it to the queue, I might be waiting, and so I wouldn't know if it's got any problems. So if I could just test it out, then I could be more confident that when it does get placed on the queue that it's going to run correctly, because otherwise I'll be back Monday morning with no data, and that would be bad. So what could I do? I will test out on Swallowtail instead of Cottontail in case a bad input, too long, other unknown problems, all the things that could go wrong. So from Cottontail's prompt in my terminal, I'm going to type SSH to Swallowtail. So this is similar to how you SSH from your laptop to Cottontail, right? So that's connecting, it's like a phone, right? So your laptop called Cottontail, which was allowed when you had your VPN open, but now you're inside the VPN. And so now you're saying, can Cottontail make a phone call to one of the other machines? It's of course not a phone call, it's an SSH line, but the idea is kind of analogous. So what we can do is we can SSH to Swallowtail. So now Swallowtail's brain will be used to do all the commands. So Swallowtail is telling its output to Cottontail, which is telling its output to you. And so what we can do then is we can SSH onto Swallowtail, and then you can CD to wherever you want to go, right? Okay, and then here's my Amber program that I'm running on the command line, which really should be in my script, but because I have my input file here, I could test it. And so if this runs correctly, then I can be confident that my other one, when I submit it to the queue, will be better. So what I will do in my input file is do 10 steps, and then when I submit it to the queue, I'll do my million steps that I actually need for the answer on Monday morning. So if you don't follow the rules and you're running your jobs on the head node, the system administrator reserves the right to terminate illegal jobs on the head node. So please don't do it. This is what you can do instead. It's best, of course, to use the queue. So putting it all together, let's take a look at what a complete script looks like. This is an example of an emin script from my lab. And so this just illustrates all the different areas that we have. So at the top, we have this shebang line that we talked about to configure. This is a bash script. So again, when you write one of these scripts, this is in fact a bash script. And so what we're going to do is we're going to configure the bsub. So I'm sending it to this queue. And I'm doing one node. This is my GPU, host span, and memory usage I'm requesting. The name of my job is this P531. And my out and error are listed here. This is the names of the files I'll be checking. Okay, we have some comments in here written by a system administrator to help us remember how to set up our scripts. And now down here, I'm going to configure all of my job-specific libraries, which I got because I know how to run Amber, that I need to use these things, and also because of the way in which I'm running it. So you see that I'm doing the MPI run, so I'm needing to use the MPI run scripts, right? So those are configured up here. And this is the actual place where I'm going to put the information to actually run a job. So I'm going to do an energy minimization, and this is how many inputs and outputs we actually have. Maybe yours is not quite so complicated, but the typical thing you would see is the wrapper script to run something. So this is going to make it be parallel. Well, this is what allows it to run parallel. And what makes it parallel is I selected pme.cuda. So this is a CUDA enabled code, which includes actual code inside of here, that will run parallel code. -O, this is actually a common flag. This is for overwrite, which allows you to overwrite if you already have these file names, like if you run this more than once. A variety of inputs and outputs that are required. So this is specific to this particular kind of a run. And so of course, you need to make sure you set all of those up. And then we have another command down here, right? So you can have as many things to do in your script as you want to do, right? So here I'm running a calculation, and then this happens to be another calculation. This is basically a really quick analysis step is what's happening here. But the idea is like, so here's my first energy minimization. Maybe I need to do more, or maybe I need to go on and do dynamics. You can, in principle, put more than one thing into the same script, or you may choose to have multiple scripts that runs each one. So that brings us back to the queuing system. So we did talk about the queuing system before. So again, your bsub is going to be what's going to set it up for the queue, and this is how you're going to set that up. The job ID is an important thing that we need to pay attention to. So when you submit your job to the queue, you're going to receive a job ID, and this is going to be useful for tracking your jobs. So here's the bsub command to send it to the queue, right? This is so bsub is the same. don't get confused, right? So B sub, the capital ones with the pound inside your script is what's going to configure it. This B sub command goes on the command line in lowercase with no pound in front of it. And that means that you're submitting your job to the queue. Make sure you use the less than sign in order to give it input. So this says the thing that comes after will be input for B sub. And so this is the name of the script that I wrote. So you would put your name of your script in here. Okay, and then it's going to submit the job. So this is your process ID. So every job that gets sent to the scheduler will be assigned a process ID, which is unique. And then that will be submitted to the queue, and it's reporting that it's going to go to the queue Amber 128, because that's the one I specified on -Q. By default, you'll go to HP 12. So then the next thing is, well, so I submitted it. Is my job running? So the command bjobs is going to be really helpful for this, because that's going to report on what's happening here. So what you can do is you can issue the command bjobs, and that will report on all the jobs that the current user, you, is running. So the information we get here is the job ID. So this will report back the job ID that you just got. This is the user, the status. So pen, this means the job is pending. So right now this job is not yet running. When it actually is calculating on a back node, then this will change to run. This tells which queue that the job is in. So even when it's running, it will have come through a particular queue. So this will report the queue. The from host is where you sent the job from. So right now I am logged to Cottontail. So it's going to say Cottontail. This is for the execution host. So the execution host is going to tell which node is actually calculating it. So you'll see like an N1 or N78 or N something. If you go back to that list we had before in the previous lecture, then it actually said which host numbers go to which queue. So you can verify that your execution host was actually something that came from your queue, so you'll know which machine you're using. And so that's what's reporting to you which machine it actually got assigned to. This is your job name, that's from your -J. And the submit time is the actual time that you typed the B sub and sent it off. So this can be useful to know, like, okay, so how long have I been waiting in the queue, or how long is the job running? So that will just keep track of when it was submitted. So the sysadmin input also uses information if there's too much traffic in the queue or something like that. So for those of you who are impatient, you know, you submit your job and it's pending, and so how long will I have to wait? Right? That's the next thing we want to do, checking the traffic report. So the basic answer is there's no way to tell exactly. We don't know how long it will be, but that's not a very satisfying answer. So you can actually get some clues, and you can rationalize some things out by using the BQs command, which can give you some ideas to watch the progress of your job and what else is going on here. So you can do this this way. So I'm going to use this to glean some information about how long I'm going to have to wait. Okay, so I just submitted my job, and I know that I submitted it to Amber 128 because that's the queue I sent it to. So I'm going to do this BQs command, and it turns up this nice little table. So don't take my word for which queues are on the cluster, right? I gave you the table, but you can use this, and this is actually reporting in real time which queues are open and active on the cluster. Okay, so it's going to tell us some important information, right? So this is just about the priority of the queue, which we're actually not really using because we're using the -Q flag in our system. The status is telling us that these queues are working, right? So if Hank turns off a queue to be doing some testing or maintenance, then you may see that a particular queue is down for a day or something like this. This is how many jobs can be in that queue. This is giving some stats about how quickly about how many jobs can be in here. The important things we need to look at here is this, the N jobs column. This is how many jobs in total are on that queue. So what I can do is I can look here and say Amber 128. All right, there's 5 jobs in this queue, and 1 job is pending. Well, that's me because my job's not running, and there's only 1, so it's got to be me. So what that means is that there's nobody else in line in front of me, so that's good news. How many jobs are running? Well, I see there's 4 jobs running. Well, that's a little peculiar because if I look over here, this says that there could be 24 jobs here, and so only 4 are running. So why am I still in line? All right, so to understand this question, you need to understand a little bit about the system resources, and that's probably what's going on here. So when we understand that we requested a GPU, okay, so when I set this job up in my -R line in my B sub, I said I needed a GPU. And so I know that on AMPER 128, there's only 4 of them. Okay, there's 4 GPUs and a single node, and that's the setup here. So what this is saying that there are 4 people running. Now that doesn't prove that they're all running GPU jobs, but the fact that I asked for one and there are plenty of open slots and I didn't get a slot yet is probably indicating that these are also GPU jobs. And I actually know who's running these jobs, and I know for a fact that those are GPU jobs. So that's exactly what's happening here. So when you request resources that are not available or are already in use, even if they're open slots, you may not actually get to calculate right away because the resources you need, GPUs, memory, or whatever constraint you put, that might be what's causing the job not to actually start calculating. But you see that you can kind of do some detective work from this little table and you can find out quite a lot. And so as you get a little bit more comfortable with this and you get more comfortable running your programs, you can kind of like use this BQs to give you an idea of where you want to send your job. So for example, maybe when I want to do an analysis, like I don't really need that much resource. So although I usually use the AMPER 128 queue, I might say, okay, but I just need to run some analysis. I want, and suppose AMPER 128 has a huge line, maybe N is, 50. I say, oh, I don't want to wait in line. What else could I do? And I look and I say, oh, but look, HP12 has, let's see, no pending jobs and 184 slots, and I don't really need that much resources. Maybe I could just run it in HP12, right? And so that's something that you could start consider doing. So be cognizant of the kinds of jobs you're running and be aware of what alternate queues you could use, because then you can start to use this to your advantage to put your jobs in other places. So just some FAQs about queuing. We already kind of addressed this. There are open slots in my queue. Why am I still waiting? And the answer is because it's probably about to do resources. How can I get my job processed faster? If you see that you could go in a different queue and you're waiting in line and you are able to move to another queue, you could consider killing your current job and then sending it to a different queue. What if you forgot your process ID? Maybe you need your process ID to do something, like send it to a different queue. You can use your bjobs commands. Remember, the bjobs will list out all of your jobs, and your process ID is one of the things. So if you don't remember your process ID, you can go to that. I need to stop or pause my job in the queue or while it's executing. How can I do this? So why would you need to do that? Maybe you need to let somebody else by. Maybe you want to stop running your job altogether. You realize, oh, I made a silly mistake and used the wrong inputs. It happens. I don't want to spend the next week blocking up my GPUs calculating on, something that's not right. I need to stop my job. Okay, so you should never outright just cause your jobs to stop. What you need to do is you need to suspend your jobs, and the way that the commands are called can be a little bit confusing as to what actually you're doing here. Okay, so stop means pause, and kill means terminate the job. So you can see that there could be a bit of confusion here. So it's important that you do them in the right order and that you do all of them. So if you issue a bkill command to terminate your job altogether and you haven't suspended it yet, you run the risk of setting up a zombie process. So what that means is it will continue to show up, but in fact, no job is actually running. And you can actually bind up resources sometimes with that. So it's really not a good idea to do that. Unfortunately, you're able to do it, but you really shouldn't do this. And when you create a bunch of zombie processes, it causes the sysadmin to have to go in and kill the zombie processes. So please don't do it. Our sysadmin will be very appreciative to just follow the correct procedure. Okay, so suppose you want to pause your job and you want to kill it or rerun it at a later time. So what you need to do is you first need to suspend it. So the way you're going to do this is you're going to use the bstop command, which sounds like it's going to kill the job, but actually it, like I said, bstop really means pause. So you're going to do the bstop process, and then you give the process ID. And again, if you forgot your process ID, that's in the question above. So you do bstop and the PID to pause your job. And then once it's paused, you can do something else. Okay, so in this case, so once you've done that, you will see a suspend. So it usually is going to be like you suspend. You may also get a different letter as well. I saw P suspend yesterday. But basically the idea is instead of running, your job is going to be suspended. And this may take a few moments to take effect. So you want to make sure you check that with bjobs before you go on and type the next command, because you may have done your due diligence to do your bstop, but you actually it's not actually completed yet because it takes a moment for the scheduler to change the status. So then after you've gotten into the suspend mode, you can either kill the job, which really will stop your job. Your job will not be running if you kill it. And so this ends the execution and it's not running anymore, even though it didn't finish. And that you have to do with bkill. So you do bkill with process ID. So again, make sure you first do the bstop and the process ID, and then do the bkill and process ID to avoid making zombie processes. And you don't type these angle brackets right inside this thing, fill in your process ID. You can also resume your job. So if you've suspended your job and then you realize, oh, wait, no, I didn't mean to do that. Your job's not over, you have another chance. Or sometimes you want to suspend for other reasons. And so what you can do is you can resume your job with bresume and the process, that's process ID, not process SID. Verify that it worked, again, by using your bjobs and looking at the job manager. So if your job is no longer in the queue, then it's not going to be in when you do bjobs anymore, right? It'll not be in the list. And so if you do bkill, you're expecting that it's going to drop off the list. And if you're resuming your job, you would expect that it will switch from the suspend mode into the run mode again, and it would be continuing on running. Even more FAQs, what if other users are in the queue? So you can do bjobs with -u, and you can see what other users are in the queue. And if you need the results from a colleague's job, is it done running, right? So you can check for all jobs being run, again, using a similar strategy. And finally, what to do when a job fails. My job didn't run. That's probably the most common thing a student would say to me. I don't know what to do. My job didn't run. Okay. And so the questions I'm going to ask are, okay, well, so, you know, what went wrong, and to try to help students become more independent at debugging their own jobs. So the first thing that needs to be discovered is the problem at the level of your execution script, or is the problem at the level of your program, right? So at the execution level, the issues are going to be something like you didn't allocate the hardware correctly, maybe you didn't allocate enough memory. It's probably a problem with your B sublines. And so if you get an error that has to do with that, then that's where you need to go to fix the problem. If you can also get issues there, like a file does not exist. So if you specify some input file and you made a typo and that file doesn't exist, you can also get an error there. So obviously the problem with that, you need to correct your typos. And so some of the ways we can discover these kinds of problems is reading the error file specified on the -e, and also you can look on the output, the -o. So you want to go and look in those files that the system is putting out. You can also look for issues from your program, and so those, if your program prints something out to the standard output, you'll find that in a -o. But your program probably has its own native log file of some kind. So what you want to do is you want to make sure you read the output of your actual program itself as well. And that can help you figure out, like maybe you had a problem with your program, or maybe there was an actual problem, with the science that was involved, like so it may be legitimate parameters in terms of writing an input file and syntax, but maybe like it's too much energy. Your system has too much kinetic energy. The energy equations blew up. Okay, that would be an example of something that needs to be fixed by fixing the science. But by knowing which output files to look in and where to look, and sort of like how that correlates back to where the input came from, can really help you debug your scripts much faster. So then that brings us to the end of our day 3. We have done a series of 3 days. We talked about first look at HPC. We worked on the cluster with text editors in day 2. And today we've talked about scripting in various forms with a particular focus on doing bash scripting for submitting jobs to the queue. So we hope you found this series to be useful in getting up and started with working in UNIX, and in particular using our cluster. We'd like to also invite you to some of the other summer workshops. These are some of the other additional workshops that I will be offering throughout the course of the summer. Next week will be molecular visualization with PyMol and VMD. We'll also have data visualization with Python, data analysis with MATLAB, Python programming for Raspberry Pi. That's a new one. We're going to be learning how to use mini computers that are microcontrollers for robotics, and we're going to have opportunities for you to actually get a microcomputer and learn how to program it. This will be the first workshop in a series that will need to continue when we go back on campus. You can actually work physically with the Raspberry Pi, but this will be the first step. And also we have a series coming up. There will be, again, another co-sponsored one with the with QAC that's going to be Introduction to Machine Learning. All right, so it was great having all of you with us, and we hope that you will be planning to attend some of our other workshops. Thank you very much, and we look forward to working with you again.